Sometimes in your search for happiness, you ponder the meaning of your life.
What is the answer to this great riddle, this enigma of the past?
Who am I? How did I come to be?
I don't have all the answers.
Look at all the innocent people.
People glorious and arrogant, valiant and headstrong.
Good people, happy people who live quiet lives and love each other.
Who suffer through no fault of their own except that they just happen to be alive.
I never dreamed you could be so bitter.
It must be, so that we can grow.
And he sees in front of him all the inequities and inhumanities that humans perpetrate on other humans.
What is the answer?
It is a tale of a man and a monster.
Welcome back to the History of Being Human podcast. I'm the host, Noel Armstrong. As always, you can contact me at THOBH Podcast. That's THOBHPODCAST. Sorry, that's a little unwieldy. At gmail.com. Thank you for your feedback. And as always, thank you for listening. It's been a few weeks since the last episode. Like many of you, spring is, for me, a time to try to escape, get an early start on summer by taking a trip somewhere warm. Escaping what's been a long and I consider very snowy winter here in Colorado, which of course we needed, so I'm not ungrateful for that. But now I'm back, and it's time to continue my update of some of the early Know Thyself topics and episodes. In this episode, I go as far back, as deep as I can go into pre-human history, back to as close as we can come to the beginning of the entire universe, and cover cosmology from the Big Bang up until the development of our solar system. Cosmology is the study of the origin and development of the entire universe, so there's nothing daunting about that, of course. But in keeping with my early intention to resurrect sense and meaning from the dust of a billion factoids, which I guess is just my way of saying I want to keep at least water cooler conversant with big topics in human history, this is kind of the biggest topic of all. And at the end, I'll explain why I think it's relevant to human history. When I go through these old episodes, there's a lot of fluff and stuff I have to delete. But I also want to make it worth your time by including new material at the end, information that I didn't cover in the initial episode, updates and facts that a geek like me finds very interesting. And so without further delay, let's get to it. Today's story begins about 13.7 to 13.8 billion years ago. And it's the story of how the universe went from being just fractions of an inch across to what it is today. And how did that happen? Well, first of all, it's important to understand it was not an explosion in space. What the theory really says is that it was a rapid expansion of space itself. So an explosion of space instead of in space. And as we talked about on the last episode, you can trace the history of the universe back to a point roughly a trillionth of a second after the so-called Big Bang. And that's as far back as we go, because before that, who knows? Before that, you get into things like quantum gravity and masses and forces and densities that nobody really understands. Nobody really even knows what it means to talk about time in intervals that small. Nobody knows if time is fundamental or if it came into existence during the Big Bang. So that's as far back as we can go. Now, what was the universe like at that time? You heard Paul Sutter describe it as about the size of a peach. Now, I like that image because I can relate to it. But you know what else is about the size of a peach? A hamster. So I'm going to call it the hot hamster verse, because I think that's way more catchy than a hot peach verse. So we have this flaming rodent at 1 quadrillion degrees, a trillionth of a second after the initial events of the Big Bang. And that's about as far back as the history goes. Now, scientists hint at this and people have brought it up, but I want to make it very explicit. Space itself is not that total void, that total vacuum between things. Space itself is a thing. It can come into existence, it can be bent or warped, it can be tunneled through, it can be tied in bows, all sorts of things. Now, a few billionths of a second after this hot hamster verse, the universe goes through this incredible growth phase, and they call this inflation. The universe grew exponentially, doubled in size at least 90 times. Now, that doesn't sound like much. You're like, what's the big deal, doubling 90 times? Think about it this way. At the beginning of this period, you have this hot hamster. What is that, 3-4 inches across maybe? By the end of inflation, and inflation itself only lasted a trillionth of a second, by the end of that time period, the universe is 58 septillion miles across. So you go from a hamster to 58 septillion miles in about 1,000th of a trillionth of a trillionth of a second. And during this time of expansion, inflation they call it, obviously the universe also became dramatically cooler. Because if you have the same amount of matter in a much more dense volume, then it's hotter. And if you expand and the volume goes up, then the temperature goes down. So the temperature dropped dramatically, even as the universe was growing exponentially. And after this initial inflationary period, the universe continued to grow. In fact, it continues to grow now, but it's obviously not growing that quickly anymore. I mean, if we went through another period of inflation like that, you blink your eyes and the person you're talking to would suddenly be about 100 trillion septillion miles away from you. It could be a little disorienting. So we've talked about the hot hamsterverse. We've talked about the period of inflation, which was a minuscule time period that resulted in an incomprehensibly larger universe. So the next thing we talk about is the creation of light elements. Within the first 3 minutes of the universe, deuterium, which is an isotope of hydrogen, is made. What happens? Well, the universe cools enough that protons and neutrons can actually join together. So this form of hydrogen is made within the first 3 minutes of the universe. Then within the first 20 minutes of the universe, some of these nuclei are able to fuse together and make helium and other very light elements. But the interesting thing is that the universe was still too hot to shine. Now that doesn't make a lot of sense to us, but for the first 380,000 years after the Big Bang, the universe was actually too hot to shine. The atoms were smashing together. They were smashing together with enough force to break up into this opaque plasma. And this plasma was impermeable to light. So the universe was very dark for its first 380,000 years. About 380,000 years after the Big Bang, matter cooled enough for electrons to combine with nuclei. So at first we just had nuclei. But eventually matter cooled enough to allow electrons to combine with the nuclei. And then you had your first neutral atoms. That's that phase of recombination. The absorption of these free electrons allowed the universe to become transparent to light. So the light that was unleashed at that time, 380,000 years after the Big Bang, still exists today. That's that fossil light that Paul Sutter was talking about and is now the cosmic background radiation. It's a snapshot of this time, 380,000 years after the Big Bang. Now, so that you don't get the mistaken impression that all was light after that time, the universe went dark again for 400 million years after that initial emission of that cosmic microwave background, after that light. Why did it do that? Well, because these neutral atoms that were formed coalesced into clumps of gas that were opaque to light. So the universe went dark again, completely dark, for 400 million years. What happened at 400 million years? I like to think of this in big chunks of time. So you have that initial phase where you have inflation. Then at 380,000 years, you have recombination, and then you have that light emitted. Then for 400 million years, the universe enters a period of time that is referred to as the Dark Ages. Because the universe is just formed of these huge clumps of gas that are opaque to light, nothing's being emitted, nothing's penetrating. But what happens at 400 million years is called the age of reionization. The huge clumps of gas coalesce into the first galaxies. And this is a very energetic process. Clumps of gas coalesce into galaxies. They emit incomprehensible amounts of ultraviolet light. That ultraviolet light is so powerful that it burns away the fog of neutral hydrogen gases. And for the first time, the universe is actually transparent to light, so light can now be seen in the universe. And the universe officially leaves the Dark Ages. So during that time, like we said, the clumps of gas coalesce, they collapse, they form the first stars, the first galaxies. So when are the first galaxies and stars formed? 400 million years after the Big Bang. So they're 13.2 or 3 billion years old, some of these galaxies. How many stars, how many galaxies are formed during this time and since then? Because this is a process that has not stopped. It continues. Right now we know, or at least it's estimated, that there are 100 billion stars in the Milky Way. 100 billion stars just in our galaxy. So then the question arises, well, how many of these Milky Way galaxies, how many galaxies are there? Well, in 2016, scientists decided that there were about 10 times as many galaxies as they had initially thought, working with telescopic data. What they decided was that in the known universe, just the known universe, there are 2 trillion galaxies, making about 200 billion trillion stars in the known universe. These are just ridiculous. These are silly numbers. These are numbers that little kids make up to one-up each other. These don't sound like numbers that map into reality anywhere. And then, of course, you'll get different opinions about how much of the universe is actually known or knowable and how much of it is still unknown. So the numbers could get exponentially larger than that. Okay, so I'm going to fast forward quite a bit now. And you may not think I'm fast forwarding enough, but I'm going to go forward about 9 billion years after the Big Bang, making it about 4.6, 4.7 billion years ago. Why is that important? Well, that's because that is when our solar system is estimated to have begun. 9 billion years after the Big Bang, in some remote, nowhere corner of a very average galaxy, our solar system is spun into existence. And our sun is about 25,000 light years from the core of the Milky Way galaxy. So we're kind of spinning at the periphery a little bit. I'm sure you've all seen pictures of it. A lot of scientists think the sun and the rest of the solar system was formed from a giant cloud, a rotating cloud of gas and dust called the solar nebula. As gravity causes that nebula to collapse, it spins faster and faster. So it's like an ice skater spinning on the ice with their outstretched arms. And as they tuck, they get faster and faster and faster. So as gravity pulls more and more mass to the center of this solar nebula, it spins faster and faster. And it spins so fast that it actually flattens into a disk. Most of the material coalesces and collapses in the center of the disk. You have this protostar, which then becomes the sun. And then out in the arms of this rotating disk, you have dust. You have gases attracted to each other by gravity. They coalesce to form planets. Now, it is believed that hundreds of protoplanets were formed, but many of them were destroyed during this process or coalesced into the larger planets. Now, if you look at a map of our solar system, you notice the rocky planets are the ones that are closer to the sun. Mercury, Venus, Earth, and Mars. Rocky planets. Why are they closer to the sun? Well, because only minerals and silicates have a high enough boiling point to survive close to the sun, whereas the gaseous elements would have been burned off by being too close to the sun. So the rocky planets are close to the sun, gas planets are farther away. Why is the sun hot? Because the pressure and the temperatures became so great at the core that the sun is constantly undergoing a thermonuclear fusion reaction as hydrogen fuses into helium. In about 5 billion years, all of the hydrogen in the center of the sun at the core is going to be converted to helium, and then the thermonuclear fusion reactions will cease. Then the fusion reactions will take place at the periphery of the sun. The sun will expand to a red giant, swallow Mercury, and make the Earth completely uninhabitable, boil up all our oceans, all that stuff. So when you look at it, we're kind of under the gun time-wise. We only have 5 billion years to figure out how to either get to another planet that's inhabitable next to a younger sun, maybe a more stable situation, or live near a red giant. So as the solar system was formed, we have 8 planets. Now, I know you may have grown up thinking there were 9 planets, but in case you missed it, Pluto's been downgraded. It's now a dwarf planet. So the only planets are Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Between Mars and Jupiter, you have the asteroid belt. Beyond Neptune, you have this huge, enormous collection of smaller objects like dwarf planets, which they call TNOs, trans-Neptunian objects, and also the scattered belt. There's the planets Eris, Pluto, things that used to be considered a planet like Pluto, now considered a dwarf planet, not quite big enough to be a full-fledged planet. So it's kind of painful to lose Pluto. But think about this, we've gained so many other planetoids or dwarf planets that we never knew existed, so it's a trade-off. Before I zoom in on Earth itself and continue the story that leads up to us eventually, I want to talk about 2 very interesting either objects, phenomena, fictions, I don't know what they are. The first one is dark matter. Beginning in the 1960s and 1970s, astronomers started to think there must be more mass in the universe than what they knew of, what they could actually see. And the reason for this is that basic physics would imply that the stars at the outskirts of a galaxy would orbit more slowly than the stars at the center. But an astronomer named Vera Rubin found that there was no difference in the velocity of stars farther out at the edges of the galaxy. In fact, she found that all the stars in the galaxy rotate and circle the center at about the same speed. So something that was invisible to her was exerting a gravitational pull throughout the galaxy. And not only that, it had to be massive. It had to have a very powerful, a huge gravitational pull. And that's what became known as dark matter. Dark matter is inferred. It's not directly visualized, but it's inferred because you can see the effects of its gravity. So it doesn't interact with light. It doesn't interact with matter in the normal way. It's kind of exotic, but you can see the effects of gravity on it. Paul Sutter, as you heard in the previous podcast, said that everything in the universe interacts with gravity. And in hindsight, I wish I could have asked him a little bit more about that. I would have pushed a little bit more on that because I don't know how you can absolutely say that. But that's what he said. dark matter doesn't interact with light, it doesn't interact with other matter. You can't crash into it, as he was saying, but it does exert a gravitational force. Currently, dark matter is thought to account for about 23% of the universe. Only 4% of the universe is regular matter. Everything that we can see, feel, touch, everything. That's only 4% of the universe. Dark matter itself is 23% of the universe. So however massive stars, planets, galaxies, all of these things are, there is a matter, or several types of matter, who knows, nearly 6 times more massive than all of that put together. And that's dark matter. So far, we have 23% dark matter, 4% what we would call regular matter. What else is there? Okay, so in the 1920s, Edwin Hubble, after whom the Hubble Space Telescope is named, made a discovery about the universe. He saw that the universe is expanding. It's red-shifted, and we talked a little bit about that already. But not until 1998, decades and decades later, and very recently in the scheme of things, the very telescope that was named after Edwin Hubble discovered something that was even more amazing. Well, possibly more amazing, I don't know. But it's certainly more disturbing or disconcerting, and that is this. If you look at very distant supernovas with the Hubble telescope, you can measure that a long time ago, the universe was actually expanding more slowly than it is today. So as time goes by, the expansion of the universe picks up speed. It's getting more and more rapidly expanding. Now that doesn't make a lot of sense, because if you have an original explosion, everything decelerates. Gravity tends to pull everything back together again. So the rate of expansion should be decelerating under the influence of gravity, but it's not. It's accelerating. As time goes by, objects in the big grand scale are moving away from each other faster and faster and faster. Something has to be driving this. Something has to be pulling or pushing galaxies apart at an increasing rate. Because the farther away from us a galaxy is, the faster it's moving away from us. And whatever is doing this, it has to be incredibly powerful. Because we're talking about pulling entire galaxies away from each other at a steadily increasing rate, accelerating the rate of expansion, overcoming the pull of gravity in these distant objects. And that's something, the name that they've given that, is dark energy, pulling or pushing the cosmos apart at faster and faster speeds. And it's completely undetectable. And as you heard Paul Sutter say, astrophysicists have no idea what it is. So I'll leave that to better minds than mine, but I do want to make one point very clear. And it has to do with what I said earlier about space. We have this idea that space is just a void. We have this idea that galaxies are flying away from each other through space. Well, if that were the case, the galaxies could never move apart from each other faster than the speed of light, because nothing moves faster than the speed of light. Every galaxy, though, that's not part of our galaxy is eventually going to become invisible to us, because it is getting farther away from us faster than the speed of light. So we're not even going to be able to see the light from these galaxies. They're going to outpace the speed of light in their movement away from us. Everything except our local group, these galaxies immediately around us, is going to be completely invisible. So how's that possible? That sounds like a paradox. But what you have to remember is that these galaxies are not moving through space. They're not moving in space. It's space itself that is expanding. So put a bunch of marker dots on a deflated balloon, make little marker marks on it. They'll be a certain distance apart. But then you blow the balloon up, and the dots will get farther and farther apart. So it's not that the dots are flying relative to the surface of the balloon. They're staying right in place on the rubber, right where you put them. But the balloon is expanding. So that balloon is space, and those little dots are the galaxies. And the breath, the lung power, whatever it is that's inflating this great big balloon is dark energy. And I mentioned the fact that we now live in the epoch of dark energy. About 4, maybe 5 billion years after the universe began, dark energy began to take over. It began to accelerate this inflating of space, this expansion of space, this increased speed with which distant galaxies are receding from us. And so that kind of sums up the cosmogony, the very early history, maybe the origin, but the very early history of all that is, of us. Again, we're those pretty decorations at the far reaches of time. We're made of space stuff, and in the eyes of a physical cosmologist, we're pretty insignificant. The universe wasn't created for us, and we have no control over its fate, and it will not notice our passing. Of course, there are some problems with the Big Bang Cosmology, things that don't quite fit the data. In fact, the whole idea of this inflationary epoch, that we talked about, this rapid expansion from a hamster-sized universe to septillions of miles in fractions of a second. That entire episode of inflation was proposed to help solve some of the problems, like why is the universe flat? Why is it not spherical as you would expect? Why is the temperature everywhere the same? If the universe was steadily expanding, you would certainly expect the temperature to be cooler at the margins, at the edges. But it's not. It's all the same everywhere you look. So it's not completely without certain issues, but it is the best explanation. It seems to fit the data, has predictive value as well as explanatory value. So it holds. But look at the story we just told. A cosmic egg, a peach, a hamster. That's no less fantastic than any myth that's ever been promoted by any society in history. And yet, despite the problems, there's so much data that fits that the Big Bang is the winner. It's the dominant paradigm. It explains cosmic microwave background radiation. It explains the ratio of light to heavy elements like helium to hydrogen and denser elements. It explains gravitational ripples, cosmic red shift, darkness of the night sky, etc. And more importantly, the most important thing with science is it hasn't been falsified. There's no one piece of data that is absolutely unable to be fit into this model. And it's not for lack of trying, because anyone who can prove that the Big Bang is wrong, you get a free trip to Stockholm, $1 million, you get endowed university chairs, you get famous, you're on TV or in books, you go down in history. So there's a lot of motivation to try to prove it wrong, but nothing has proved it wrong yet. So the Big Bang model holds for now. All right, that's it for the wide-angle grand tour overview. Now for a few updates. First, in that episode, I said that we can trace the universe's origin back to about a trillionth of a second after it began. And I said before that, who knows? But I want to clarify why scientists can't go any farther back than that. The reason is this. Before that time, we have no adequate description of the laws of physics that could explain the very bizarre nature of the universe at its very, very beginning. If you extrapolate from the expansion of the universe backwards in time using general relativity, you arrive at an incredibly exotic state of things. Infinite density and infinite temperature at a finite time in the past. Models based on general relativity alone can't extrapolate all the way back to the singularity. So we begin at a trillionth of a second, because for now that's as early as current physics can model it. Another point about the Big Bang that will make you the envy, or maybe the pedantic annoyance of every cocktail party, is this little mystery. Why, if the universe was so dense, did it not simply collapse into a black hole right at the outset? In our current universe, anything even a fraction of the density and mass of the early universe would collapse immediately into a supermassive black hole. But before you think you have all astrophysics in checkmate, there's an explanation for that also. And that is that the commonly used calculations for explaining gravitational collapse are based on objects of relatively constant size. They don't hold in the rapidly expanding early universe proposed by the Big Bang. And that brings me to my final point. If you have an interested layperson's understanding of physics, like I do, you can get the idea that you almost have to make up an entirely new physics for various situations. So you have general relativity for large-scale objects. You have quantum mechanics for very small particles. You have one physics for the very early state of the universe and another physics for the universe as we see it now. And you start to realize something that experts in the field realized long ago, and that is that the laws of physics themselves are not as eternal, infinite, and immutable as my junior high science classes might have led me to believe, as I myself would want them to be. Different laws apply in different conditions and in different scales. And as of yet, we have no grand unified theory. But maybe the most mind-blowing thing that I came across, that I learned as I was preparing this episode, is that the Big Bang model doesn't just explain how space and matter and energy came into being. No, according to theoretical physicists, the very laws of physics themselves evolved in the primeval universe. Now that's hard to grasp. That's hard to get our head around. But according to the theoretical physicist Thomas Herzog, one of Stephen Hawking's colleagues, quote, "The rules of physics transmute in the primeval universe in a process of random variation and selection akin to Darwinian evolution, with particle species, forces, and even time fading away into the Big Bang," end quote. So what he's saying there is it wasn't just time and space and matter and energy. It was the rules, the laws of physics themselves that were evolving and that were then being selected in a process somewhat like Darwinian mechanics works on biological species. And this was all taking place in the very early, as he describes it, primeval universe. The implications of this are simply staggering. For example, the universe could have ended up with fundamental forces of very different strengths than they are now. An example Herzog gives is gravity. Gravity is a very weak fundamental force. If gravity were stronger, stars would burn out much more quickly because they would burn far brighter. That means that complex biological life would have had no time to develop on planet Earth, or really anywhere else in the universe. Another example from Herzog. If temperature differences in that cosmic background radiation, that relic of Big Bang radiation, were even 1 part in 10,000 bigger than they are, Herzog writes, quote, "The seeds of cosmic structures would have mostly grown into giant black holes instead of hospitable galaxies with abundant stars," end quote. This next one is really challenging for me to conceive. The universe, as it was evolving, evolved 3 large dimensions. At the quantum level, who knows how many dimensions there are? But there are 3 large dimensions of space. Add time and you have 4, but you have 3 spatial dimensions. That didn't have to be the case either. We could have had 4 or 5, or who knows how many spatial dimensions. According to Herzog, if we had even 1 more spatial dimension, the universe would have become much more unstable. Herzog writes, quote, "Adding just a single space dimension renders atoms and planetary orbits unstable. Earth would spiral into the sun instead of tracing out a stable orbit around it." And I'll just give you one more example. Carbon is essential for life as we know it. We are carbon-based life forms. Every form of life that we know is based in carbon. Now, it's not impossible there could be other life forms, silicone-based life forms, for example. But as far as we know, carbon is essential for life. The formation of carbon in the center of stars depends on the exact balance between the strong nuclear force and the electromagnetic force. If the strong nuclear force were just a fraction stronger or weaker, carbon atoms would not be stable. It would be impossible to form carbon, and carbon-based life would be impossible. So in the big picture, we are here because an almost infinitely improbable set of circumstances that evolved, that were selected during the primeval state of the universe, came into being, obtained. But here you have to be careful. When you hear how unlikely our existence is, you can easily fall into the belief that it was all meant to be, that the universe exists for us. But that is a matter of faith. That's a religious position, and science certainly doesn't claim that. Kind of a reversal of cause and effect. It's kind of like in Candide when Professor Pangloss claims that the human nose was clearly designed to be the resting place for eyeglasses. Instead, we are the natural result of the universe as it is. I like how Alan Watts puts it, quote, "We do not come into this world, we come out of it, as leaves come out of a tree, as an apple tree apple, and as an ocean waves, the universe peoples. Every individual is an expression of the whole realm of nature, a unique action of the total universe," end quote. And so there you have the rationale behind this episode on Big Bang Cosmology. If each of us, in the eyes of science, is a recent development in the process of universing, not separate from the process, then the deep history of the universe is our own deep history. And in the next episode, we're going to continue this history through the development of the solar system, the Earth, and the earliest life forms.